So, welcome back to the second part. So we had quite a few interesting discussions during the break. And I will just now finish this theoretical session with 2 or 3 important slide decks. And then later I want to do a quick start on TensorFlow and Keras, which is a very sophisticated deep learning framework. And then I will run a little demonstration of my work, so actually a real-time anomaly detector using LSTM and autoencoder. Then you see basically the whole end-to-end flow. Yeah, and then we see if you have other questions, then I can address those. Just one deck about activation functions. So activation functions are in the neural network to add non-linearity. And here you have, for example, the sigmoid, which we already introduced. You have also linear functions. And there's TAN-H and ReLU. And this is here leaky ReLU. And it's pretty simple. If you don't know what to do, you use ReLU in all intermediate layers. You use linear for the output layer if it's a regression problem, and you use here it is. You use softmax for classification. So if you keep that in mind, you're already you have a good set of activation functions. And if your neural network is not performing well, the first thing you can change is going from a ReLU to a leaky ReLU activation function. That's all. So TAN-H is not used anymore. But you have to try. You never know. It's a bit black magic sometimes. And then someone of you asked how to mitigate overfitting, so that's the bias variance trade-off. Since we have the universal function approximator, the problem here is overfitting. So in traditional machine learning, it's mostly underfitting because your model can't represent the data set. Here we have the opposite problem. And as you might know, you have a way to train the model using your training data set, and you take 20 to 30% of the data set apart in order to assess. So if your training is working well, that's already a good sign. So if you get good accuracy for your training data, and you get also good accuracy for your test data, then you're fine. And you see here illustration of overfitting. So in a binary classification setting, we have here a decision boundary, which is learned. So the green one is learned, and the black one would be optimal. And you clearly see that the green one is overfitting, and the problem is we mostly get the green one. So one way, of course, to address this problem is just simply more data. So there's this general rule of thumb in machine learning that you need 10 times more data than the number of degrees of freedom in your model. So each parameter in your model adds 1 degree of freedom. So in linear regression, this is linear based on the number of features, but unfortunately in neural networks this is exploding. Therefore you always need a lot of data. So if you have only like 1,000 samples, it's very hard to do neural networks. One exception is transfer learning. You can just Google for transfer learning, or you ask me later. But otherwise you need a lot of data. So you see here 10 times the parameters of data you need. Then regularization. So regularization is already used in ordinary machine learning. So here you again have a cost function, which here is dependent on the parameters. This is the cost function itself, and this is the regularization term. So intuitively, it takes each parameter value and squares it and adds it to the cost. So that some sort of intuitively should give you an idea how this works. That means if you have high values in the parameters, you increase the cost exponentially. So you are kind of restricting the model of learning weird things or huge parameter ranges that gets penalized. And that's a way to reduce complexity of the model. You can change the rate or the amount of regularization using the delta parameter, lambda. Then early stopping. You have here the performance on the training set, the red line, and the validation set. And whenever the error goes up, you stop training and you just stick with that model. Then dropout, that's a relatively recent invention which works pretty well. So during training, you randomly deactivate a subset of neurons. So this is now an example of a 50% dropout rate. And yeah, that's basically the most prominent ways of mitigating overfitting in neural networks.
How is dropout different from one of the optimization techniques in inference engines where we remove the nodes or we remove entire layers? Pruning, for example, how is it different from pruning?
It's different in the sense that,
yeah, it's different because in when we retrain the network, the dropout layer again comes, but in case of pruning, the neurons which we have removed doesn't come again.
Okay, so you have the answer from the expert. Which is true because dropout is randomly deactivating, whereas in pruning it's constantly, no? Yeah, okay. Good. So now let's do, who of you has worked with TensorFlow so far? No? Okay, so maybe it's first. To have a look. So TensorFlow, it's open source, it's a Google framework, and it can create static data flow graphs. So static means you define it once, and it's not changing during execution, and it's not taking any statistics of your data set into account for optimization purposes. You can express any arbitrary linear algebra algorithm with it, and you can execute it at scale on multiple nodes, and also embed it. So there's TensorFlow Mobile and TensorFlow Lite as well for inference only. So the idea is you have here a matrix multiplication operation, which is a TensorFlow operation. You have addition as a TensorFlow operation, and you have softmax, which is the activation function, which is also TensorFlow operation. You have then placeholders. Placeholders are basically parts of the computation graph which are loaded with your data. And then you have variables. Here you are computing linear regression. And then you add a bias. So that's basically the linear regression to be precise. And afterwards, after adding those two, you are applying softmax. And that whole thing is now expressed in Python. So that there's a C++ API, but nobody's using that. So everybody uses Python API to express this execution graph, and afterwards the engine does the computation. Okay, so do we have internet here?
Yes, yes. You should be looking at NIT-K.
Yeah, first of all, I need to find my Wi-Fi symbol. Okay.
What is this? 2K16 minutes. All caps.
Usually takes some time. Okay. Scroll up. Or I can use the second laptop which has it's also late. You can also go back here.
No, what's up? Or you say or
Or you can cancel it and try again and maybe do that notification. And it will not so good. Thank you. Okay, so okay, it's loading. So I just want to show you a little TensorFlow example how it's looking like in Python, but I have some trouble. It's coming.
You should also give an overview of what IBM Watson is and what Watson IoT is. Also, what are the goals?
Okay, while we are waiting, let me give you my breakdown of IBM Watson. So it all, I can show you that later if you have time, but it all started in 2011 when the IBM Watson Research Lab did, created a computer which was winning against the two Jeopardy world champions. So the computer has been called Watson after the lab. And so everybody was so impressed that IBM just created a business division which was then called IBM Watson, which has a clear purpose of AI. And that's the generic term Watson. And basically everything which comes out in that space now is somehow called Watson. So after the Watson unit, the second unit has been created, IBM Watson IoT. Where I work for, and the third one, IBM Watson Health, and also the complete tooling in which we have is somehow called Watson. So this is called Watson Studio, but it's a marketing name. It's not a specific product. So let me just find the notebook. Here. So this is based on Jupyter. Jupyter is the open source environment which is heavily used in data science, which is a notebook where you can have code and the result of the execution of your code is shown directly in the notebook and also any sort of visualization. So we are now taking here an example of the MNIST dataset, which is a handwritten digit recognizer. It's coming from a K-bill competition, and let's have a look at the first image. Whenever you see a star in such a notebook, that means that the background process is still running, and then if you see a number, the process has finished, and if you have created some output, you will see it here. You see here that's TensorFlow version 1.11. Here I'm running some imports, so that's Python overview, knows Python. Okay. Yeah, anyway, I assume you all have C++ skills. So it's far more simple. I think the main difference between C++, Java, and Python is the way how to express blocks. So in C++ you have curly braces, and in Python you have just idents. So now we are downloading the MNIST data set, and here this is now 4. So this is a 64 by 64 matrix, which has a value range between 0 and 255, indicating the intensity of the color. So this is the feature map, and this is the label. So this is a one-hot encoded vector where you have here 1, 4, 4. So 0, 1, 2, 3, 4. Element 4 is 1, that means this is a 4. So let's read it again, because we reset then the random generator, and let's have a look at the TensorFlow code. So here, the first line, so as I said, it's just a domain-specific language in Python which is used to express the TensorFlow execution graph. Therefore, it looks a bit weird. So you have here TensorFlow placeholder. This creates a matrix of type float 32 with an undefined number of rows and 784 columns. So 784 is basically 64 by 64. That's the input image. So this is the training data, X, and then we define W and V. Those are the parameters of your regression model, and then you apply the softmax function again to this. You see here that's X by W, which is obvious, and then we add the bias, and you see here we are using, or TensorFlow uses operator overloading. So this plus here is not a plus operation for integers in Python, it's a plus operation on top of the node in the graph of TensorFlow, and that's basically it. So we have a placeholder for the training labels. Now we initialize the gradient descent optimizer, and now we are training. So in batches of, so the MNIST dataset has 60,000 training examples in 1,000 batches. So after 1,000 examples, we update the weights, and then we do another 1,000, and we get a random distribution from those. So there's a, see here, there's a next batch function, and sorry, the batch size is 100. So it's 1,000 times this, and you have 100 batches, so 100 images you train on, and then you update the weights. And this is now running in the background. In a Python process, the Python process starts or encapsulates the C++ program which is executing the graph, and then after some time you will get around 92% of accuracy. That's what you get with a softmax regression model on the MNIST dataset. So this is TensorFlow. Let's leave this running, and now I want to show you something else. Because you might have seen that we are here working on matrices and so on. And in neural networks, we are thinking more of layers. And you see here, actually it's a bit weird because Keras is a high-level framework which can use TensorFlow as underlying execution engine. But now the main developer of Keras, he is now a Google employee, and there's some sort of mixing in Keras into TensorFlow, which I think is not a good choice, but it's highly political. So because TensorFlow is lacking the high-level capabilities, they are squeezing it into TensorFlow. But anyway, it's very simple. If you just remove gf dot, then you basically get the same code for Keras. So the idea here is you create a model, and you add a layer at the first. So that's the input layer. It has 512 neurons, and the input shape is a vector of 784 dimensions, so it's actually also flattening the images into one single vector. You have here the activation function of that layer. Then you already know what dropout is, so in each iteration 20% of the neurons are deactivated, and then you have a fully connected dense layer of 10 neurons because you have 10 classes, and you have the softmax activation function which is the one you use if you want to predict one-hot encoded vector, which you are using in multi-class classification. You have optimizer, so I haven't told you about the different variants of gradient descent optimizers. If you're interested in the Coursera course in week 1, I'm going over different optimizers. So they are highly influencing your accuracy, by the way. And then the cost function you can define, and the metrics, you say model compile. And then the training is simple, you say model.fit, and training data and target. And then you can either evaluate, or you can just say model.predict. You can also import export models, so you can write the parameters and topology to files and read it from somewhere else. Okay, so that's like a fast track introduction to TensorFlow and Keras. So let's spice chat, right? Too many windows open. Then I want to show you 2 other things. So one is TensorBoard. So neural networks are pretty hard to debug, but at least TensorBoard and similar functions we have also in our cloud in Watson Studio is a way to open the black box and this is done by plotting interesting graphs. So the most interesting graph obviously is loss over iterations. So loss is the error you are doing. It should go down and it should always look a bit like this. Okay? It's okay to have oscillations. The oscillations come from the policy where you update the weights. So you can update the weights after one complete epoch, where you have shown neural network all data, or after each example. So if you update the weights after one epoch, it's called gradient descent. If you, it's called batch gradient descent. If you update it after each training example, it's called stochastic gradient descent. And there are different variations of that. Then you have here, for example, an easy way to debug your neural network training. If you have such a trajectory, something is wrong. Either, for example, the learning rate is too low in the blue line, or the complexity of your model is too low. It cannot fit your data well. There are different ways to see that, but actually you have a problem. Here it's working, but the learning rate is maybe also too low, but also here the blue line might indicate that you have an overfitting problem if it's just going down so fast. Then 1 over loss is accuracy, more or less intuitively. So accuracy should look like this in the ideal case. Now you have some sort of a histogram in neural network debugging where you show the parameter distribution over time. So you have here the start of the training, it goes down to the end of the training, and you see here that's a relatively ideal parameter distribution because they are not at the edges, so that's good, and they are all centered around 0, that's also good, but they shouldn't be 0. If you have 0 weights, then you are losing the gradient and it doesn't work. So those should be close to 0 but not 0. This is an example of the value distribution of the output layer. So remember, we have a one-hot encoded target vector, and therefore we also should resemble in something like this, which means that most of the times the value in the target vector is 0, and a couple of times it is 1, and in between you shouldn't have something. You see here, gradually during training this distribution gets better and better. So that's the way how to debug neural networks. And finally, the reason for all that hype around TensorFlow is not a linear algebra, it's the automatic differentiation. So you have, for example, the first derivative of cosine x is minus sine x. And the way how, so you see here, if you have cosine of x, you have here minus sine x, that's 0 gradient. Then you have the maximum negative gradient, so that's minus 1. Then you have the maximum positive gradient, and here you again have 0. So that's the first derivative of cosine x. And the way how this is done in TensorFlow is that each operation, so each node in the graph, has to register its first derivative function. And here in that case it's minus sine of x. So this node here is the gradient of cosine, and this is minus sine of x. And using the rule for partial derivatives, TensorFlow can automatically construct the derivative of each and every graph you are expressing. That's the cool thing. So you can come up with any linear algebra, any type of neural network. TensorFlow automatically creates the first derivative, and that's how it looks in code. So you register a gradient function for the zero out operator, which looks like that, and then from that time on, TensorFlow knows how to take the first derivative. Okay, so now some more hardware related. Just show that quickly. So all the data I'm analyzing is usually coming as a sensor stream on an MQTT message broker, which I'm subscribing to, and I'm doing two things. I think you asked the question, no? So I'm storing all the data, mostly in object store. That's the cheapest way how to store data, in a format called Parquet, P-A-R-Q-U-E-T, which is a column store format which uses compression for saving data and for accelerating access time. So that's so I'm basically always storing all the data, all the raw data. The reason is that we can come up with better models, better ideas, and then if you don't have the data is lost. So data storage is so cheap that we always should store all the data if possible. And then in addition, we have real-time engines. I'm just showing you one here, which is open source, that is Node-RED, which is developed in my team, which is running on Node.js, and it gives you graphical data flow graph, and also you can add user interface. So that's pretty cool for all type of sensor processing. And currently we are also working on getting TensorFlow, Python, all the stuff running in it. So using this tool, I've now created a little physical model, which is the Lorentz attractor model. So Edward Lorentz was a pioneer in chaos theory, and he found out that a simple three-formula model for x, y, and z already creates chaotic data. So we have here 4 constants, h, a, b, and c, and 3 variables, x, y, and z. And here, in each time step, we are updating x based on h, a, b, c, and y, x, y, and z. So you see that here. And that's basically it. So if you now create that trajectory, that time series, you get some sort of this data set, which is an ideal simulation for example for accelerometer vibration sensor data. So that's the time series plot, and now I can change the parameters of the Lorentz attractor model to have 2 distinct classes, so 2 distinct time series patterns. So this is one, this is the second. And now I'm applying LSTM. So LSTM, as I said, is mapping sequence to sequence. So there's one to one, one to many, many to one, many to many. And here many to many can also be shifted. So from the past n data points, you predict the future m data points. And using, also that's something you asked, you can do 2 things using that. So one thing that I'm actually stuck with in IBM is the anomaly detection algorithm, which is working surprisingly well. which we are using in different client settings for anomaly detection in PMQ, predictive maintenance and quality. But the second thing, which I haven't explored so much, is time series forecasting, because since you can here create sequences, future sequences from past sequences, you can use this ideally for time series forecasting. Also, that's another way for anomaly detection. If you forecast your time series and then you take the difference between the real future values and the forecasted future values, you also have some sort of anomaly detector. That's another approach, but I'm using the autoencoder one. And you see here, LSTM is that powerful that you can now train the LSTM model with half of a sine wave. And you see here, the training data only has positive or zero gradients, and then the sine wave which has been predicted is having negative gradients. So that's really a black magic, no? Yeah, that's basically the result of the anomaly detector. So you have here two batches of normal data, one batch of anomal data, and you see here a very high spike in reconstruction error. And that way, if you have such a high spike, all that part here can have contain noise, and you still will see the spike. That's why it's so important to have such a high spike in an anomaly detector. So all that stuff I've already covered, training, great descent. So now my task is to scale this, because as I mentioned, neural network training, so we are training here in an anomaly detector, we are constantly training, is very compute intensive, and factories have a lot of sensor data. They have thousands and thousands of sensors, and the problem is the scaling. So here I have Google Trend charts, and you can guess which search terms I have used, if you like. So there's a red one and a blue one.